Hello everybody and welcome back to the Pie Show. We're on episode 3 now, which is talking about how everything is electromagnetic. Truly an exciting episode to be filming. I wanted to dedicate this episode to my favorite human being of all history, the most inspirational character for me. He was truly an innovative inventor, and then he's known as the inventor of the electrical age. His name, Nikola Tesla. He's obsessed with the number 3, so I figured episode number 3 is appropriate for him for this episode. So I'm going to bring it to you. I hope you enjoy it. Alright, so I'm going to try going back to putting this video into 3 parts. Put this video into 3 parts. We're going to have the first part's going to be about basically how we discovered things like gravity and electromagnetism, like the timeline of discovery. Part 2 is going to be more so about basically we're going to be talking about equations, basically how I see electromagnetism and gravity and things like that, and how everything is electromagnetic. I'm going to try to produce that idea out there. Part 3 is going to be much more interesting. It's going to be basically how UFOs work, how I see, alien technology. Alright, we're just going to start with this timeline here, and we're going to be starting over here in 1687, about Isaac Newton. And this time he published Philosophiae Naturalis Principia Mathematica, which was about gravity and physics. And Isaac Newton's a really wonderful and incredible guy in history. He helped figure out how to do calculus, and he wrote the book about gravity. But there's just one thing that's sad about Newton, is that he never got around to really understanding matter. That's not necessarily true. He understood matter pretty good, but he didn't quite completely understand it as good as other humans figured it out later on. So the next part I want to go to is about 1803. And this is when John Dalton, he discovered that, different elements cause there to be different types of atoms. Right, and then after that, in 1904, we have J.J. Thompson, and he discovered electrons in atoms. And he discovered that they have negative charge, a negative electric charge, with this plum pudding model. And after that, in 1911, we have Ernest Rutherford, and he discovered that atoms are mainly empty space, and on top of that, also found out that there is a positive charge in the middle. And he did this in a pretty cool way. He used gold foil, and he shot charged particles at this gold foil, and most of the time they just go right through the gold foil, but sometimes they bounce off, and that's how he figured that out. And then in 1913, we have Niels Bohr, who discovered electron orbits and orbitals. And after that, in 1926, it's Erwin Schrödinger. Very cool guy. Discovered electron clouds of probability. Now what's cool is back in 1687, Isaac Newton was able to discover gravity without knowing basically any of this stuff about matter, but he knew that matter was involved. Now what's interesting is, currently in our time, we look at gravity the same way that Newton used to look at gravity, even though we've learned all this stuff about matter that Newton didn't know back when he discovered gravity. Alright, now I'd like to show that this timeline here was meant to be, more about matter. Now I'm going to make another timeline down here, and this timeline is going to be more focused on forces. The forces of nature. So we're going to start, let's start in the same place, I suppose. 1687 with Isaac Newton, who discovered gravity. Pretty big deal. Very big deal. It led to motivation of a lot of things. I will write Newton up here. Just make sure he doesn't feel left out. Now, next, after that we discovered, in 1873, James Clerk Maxwell. And he wrote, a treatise on electricity and magnetism. which basically had a lot of information on the electromagnetic force. Right, and then after this, we have in 1933, we have Fermi, who discovered something called the weak interaction. Also, when he discovered it, he called it Fermi's interaction. And then after that, in 1968, we have a bunch of guys. We got Sheldon Glashow, Abdus Salam, and Steven Weinberg. And these guys, all three of these guys together, in 1968, they discovered that basically the weak interaction and electromagnetism kind of work together. So basically, they discovered that the weak force has to do with electromagnetism. So both of these guys together kind of figured out the electromagnetic weak force. And lastly, after 1970, and I couldn't find a ton of information on this as to who specifically sort of figured this stuff out, but we learned about the strong force, and it has a lot to do with quarks. And quarks are like they're little fractions of subatomic particles. So like each particle, like proton, neutron, they all have 3 parts to them. And they are known as quarks, and they have fractional charges. And it's pretty interesting, and this is sort of the explanation as to why the nucleus of the atom doesn't push itself apart and explode itself. Because that's what you would think would happen if just a bunch of positive charges was all in the same area. And this is also known to be electromagnetic. So we have 4 forces total. These are all the forces of nature, and all of them, the point of my video is that all of these are electromagnetic, but we didn't think that gravity was electromagnetic because we discovered it first before we really understood electromagnetism. Alright viewers, so here we are in part 2. This is the explanation of how everything is electromagnetic. Now this is true because everything is composed of matter, and matter is electromagnetic. Now, electromagnetic fields are caused by flux in electric fields. Electric fields are created by electric charge. Now when it comes to matter, subatomic particles, being these guys, all have electric charge constantly, and thus they create electric fields. Electrons orbit the nucleus of the atom, thus they fluctuate back and forth, causing electromagnetic fields. Now, the way that gravity works is it is kind of magnetic because matter is electromagnetic. And so I got magnets here to kind of point out we got the positive side and the negative side of a magnet. Obviously they will attract, right? And they could do that at a distance. And the negative and the negative would repel, and they would do that, but they do it better because you can feel it here. If I put them close together, it's a larger sort of repulsion force. Now, if we put them in a certain orientation so that negative is against negative, these guys will flip over, and this is with gravity as an aid, but they will flip over and attract. And they always do this. They will choose attraction over repulsion no matter what. And that is pretty much how gravity works. Gravity has both a force of attraction as well as a force of repulsion. Now, you might think that what you've heard from gravity is that it's only an attractive force, but it is necessary that it has a repulsive force as well, so that we don't, fuse with things. So like right now, me standing on the planet, my feet would be fusing with the Earth if it was only an attractive force, but because of the force of repulsion, the electromagnetic barrier that atoms have is what causes us to be able to sit atop the Earth and even jump if we wanted to do that. But the attractive force is greater at greater distances, and the repulsive force is greater at lesser distances. And so here I'm going to show you how gravity works when we are looking at the hydrogen atom. And this is just to keep things simple. I don't want to have a bunch of electrons and a bunch of protons and neutrons to have to explain about, but Point is, because the proton has a positive charge, it attracts the electron with a negative charge. So these guys draw each other closer. And same thing with this proton and this electron. And this attractive force is very strong. And also there's a repulsive force between the protons. They would be, like charges would repel. And the electrons do the same thing. However, the point is, these guys could get real close to each other if they're far apart, and then the repulsive force would keep them from fusing together. And it's only within things like stars where things do fuse, and that's nuclear fusion. That causes all sorts of things. We're going to be talking about that in the next video. For now, we're focused on, gravity. All right, now, the force of gravity is this guy. This is the equation for the force of gravity. This is the equation for the force of electromagnetism. And you will see the similarities between the two kind of point out that they are pretty much the same equation. These m's here are mass, these q's are electric charge. The thing about matter is that all matter has electric charge, so pretty much just convert these m's to q's. R is the same of both equations. It is the radius or the distance between the masses or the charges. And these G and K are pretty much just the same thing. They're just scalar multiples, and it's depending on, like I just write C for that. But, in reality, these aren't the same number, but they're scalar multiples. They're there to basically size the equation and to put the right units in the place so that you can think of it as a force. And when it came to this discovery of the force of electromagnetism, we thought of it basically in simple terms where we just had one charge. We had, one singular charge, not like both charges put together like in atoms. And so I think that's why the scalar multiple is kind of stronger than is the scalar multiple for force of gravity. And that's why the electromagnetism is thought to be greater than gravity, but gravity has, push and pull involved, and I think that's why it's thought as like weaker than electromagnetism. But you have electric charge, you have a positive and a negative. This negative will be attracted to the positive, and if you had two positives or two negatives, they would force each other away. And this is kind of what the electromagnetic field lines look like for these types of situations. This is why matter attracts matter, is because it's electromagnetic. The laws of electromagnetism apply to matter. Also, if we were to understand that everything is electromagnetic, then this would help us understand the grand unification theory. Light is electromagnetic radiation. Alright, so lastly, we're going to talk about how photons have electric charge. Now, if you were to research this online, you would see the exact opposite of that. You would see that photons are thought to have no electric charge. Now, for me, I see a contradiction in that because photons are thought to be a quantum of electromagnetic radiation. As we were talking about here, light is electromagnetic radiation. Now, I don't see how this really could be true, that photons have no electric charge and they could be electromagnetic radiation, because you can't have electromagnetic fields without electric charge. Also, neutrons used to be thought to have no electric charge, but then later we found out that quarks show that neutrons do have electric charge. Now, I used to think that electrons also had quarks, but I found out that they're leptons, and that just means that the strong force doesn't really interact with electrons. It only has to do with protons and neutrons. Neutrons do have electric charge. They're just fractional, and that's what the quarks are. That's what these three little, circles are. These three little circles are to represent the up and down quarks. Up and down quarks are basically here, like the plus 2/3 charge, those are meant to be up quarks. And the negative 1/3 charge, those are down quarks. And neutrons have two down quarks and one up quark. Protons have two up quarks and one down quark. And that's what gives us the positive 1 charge for protons and the plus 0 or plus or minus 0 charge for neutrons. But we still have electric charge within neutrons, just like we have electric charge within photons. Thus, everything can be electromagnetic because everything is electrically charged. Alright, so we made it to the final part. This part of the video is going to be about alien technology. So the first thing we're going to talk about is going to be the tractor beam. Just going to draw our little flying saucer guy. You know, we got our little alien guys in here. The big heads. And then they got the tractor beam coming down on a little stick figure guy. And basically what this tractor beam does, what I think about it is because, you know, as we were talking about earlier, light is electromagnetic radiation. So I'm just going to write EMR. Basically what this means is, so when light comes down from out of their ship, even if it's created from a source that somebody else makes, it would cause the air and everything around it to become, these little signs are going to be negative signs. It's just going to cause everything to become negatively electrically charged. And then because of that, this little dude, if he's negatively electrically charged and so is the ground, then this will cause electromagnetic repulsion, which will cause him to push off the ground and he will start floating up. But then the reason that he's floating up isn't just because of the ground being negative and him being negative, but also probably within the ship have some positive electrical charges going on in there, and I'm sure that would be something that they would control. And then because of that, you would see the electromagnetic field lines would look kind of like this. So you'd kind of first be pushed up, and then on the outside you'd be pushed down. So like there might be like, you know, if like say there's like a tree nearby or something, it's got all of its leaves and whatnot. Like the leaves, if there might actually be some leaves just like coming down kind of quickly if they're outside of this beam. That's kind of what I assume would happen, because this is the way that electromagnetism works, and then this would even cycle back in like that. That's just kind of how magnetic field lines work. That's the impression that I get about tractor beams. Alright, cool. So the next thing we're going to be talking about, and this is the last bit of this video before the outro, we're going to be talking about something I call it this for fun, but the Trifecta Theory. Alright, alright, so I call it the Trifecta Theory because it's basically like three theories rolled into one, sort of. Like they could very well affect one another, and we're talking about this specifically more so about the travel through space-time, kind of using electromagnetism to your advantage, and then we're going to be more so focusing though on the Earth and how you could get away from the Earth's gravitational field. So the first theory is called the curl vector theory. So the curl vector theory has everything to do with the curl vector. If you don't know what it is, it's like, we talk about it like this. It's like one of the right-hand rules. If you have something moving in like a counterclockwise fashion, then there'd be like, you know, your thumb would point in the direction of the vector. So like if you had something going like that, that's what we're talking about. Then a vector would come out of the point like that, and it would be perpendicular to the circle. And, you know, the other way would be true as well. If you had it come like that, you know, if we had the circle going the other way around, then it would point the other way. And this is kind of how like fans work. This is how like helicopters work. And the idea here for the curl vector theory is we would talk about basically like a, you know, how you would use a tornado of electrons to basically get yourself to move away from the Earth. So basically just need a large amount of electrical wire. Let's see if it was going like that. So we're talking about going like that. So that would push downward. You know, let's say this is the Earth's surface. You'd want to have something, you know, pushing downward, you know, away from your ship so that your ship itself can move upward. Alright, the second of these two theories would be the standing wave theory. Alright, now the idea behind the standing wave theory is, if you know anything about the standing waves have to do with waves, obviously. So let's say we have a bunch of waves going this way, and we have a bunch of waves going the opposite direction. If they're at about the same frequency, then it is possible that these waves could either add to each other and they could become bigger, or they could subtract from each other and they could become smaller. Or they could completely cancel each other out. And the idea behind the standing wave theory is that you, for this instance, for traveling, you know, getting away from the Earth, It'd be that, you know, basically the Earth has its own sort of signal that it sends that says, hey, you know, come here, like pulls everything in, and that's gravity, right? Now, if there was a way that you could block this signal, maybe gravity wouldn't have an effect on you anymore. Wouldn't that be cool? Now, the only way you could really do that would basically be if you could send out a frequency of waves, say you're here, you could send out a frequency of waves that interacts with the frequency of waves that is the signal of gravity. Basically, if you could send out your signal to the same matching signal that the Earth sends, maybe you could use the standing wave theory and cause these two waves to cancel one another, and then that way you wouldn't have to worry about gravity being so strong anymore. And also just wanted to point out, you could also use the standing wave theory for the opposite purposes. Say you're really far away from a physical object and you want to get there quicker, you could send out a resonant frequency to that guy and then hopefully get the adding to each other part of the waves, and then that way your sense of attraction would be increased so you could go faster towards a physical object. Alright, so the third part, the third theory, is what I like to call, also for fun, I like to call this the flux capacitor theory, right? Because they talk about flux capacitors in movies with time travel and whatnot. So basically the idea behind this is that you would want to have a capacitor that could really do a good job of holding in like electromagnetism, or, you know, flux in electric field, right? So say, you know, we had, basically the way I think about this is if we had, you know, a really strong Tesla coil. So if you have these two different types of coils, you can kind of cause there to be electromagnetic field. And with an electromagnetic field, this is, you know, basically creating the electromagnetic flux. And if you could sort of maintain that, if you could maintain, this is like sort of the symbol for, well, I don't need the arrows, but this is a symbol for a capacitor when you're looking at diagrams of electric stuff. If you have a really good capacitor, you could hold a large amount of electric charge. So say that you had some sort of ship that had a great capacitor for flux, then you could basically shoot out, you could discharge your capacitor, and by doing so, that release of energy could cause you to resist gravity. So like, you know, if I were to use the energy equations that I've learned from physics, we would be using, you know, we'd have electric potential energy plus gravitational potential energy. And this would be equal to, same thing again, but like basically like the after effect. So say, for instance, you start on the ground, so your gravitational potential energy, which would be written as mgh, and it's the same thing here. If we start on the ground, there, h is at 0, so this would be 0 at the beginning. Now, if your electric potential energy was a bunch at first, I don't know what number to use for this, so let's just call this x. Okay, now, let's say you got rid of that electric potential energy, it goes down to 0, then this would increase your gravitational potential energy to about x, which would be mgh, your height would be y. And this would change because you would dissipate your electric potential energy and trade it for gravitational potential energy, or height, or distance away from the Earth. Now, with this flux capacitor theory, I just wanted to point out that, you know, in order to do this sort of thing, you would need to not only be able to have a high capacity for electric potential energy, but also you'd have to be able to maintain or like regain electricity while you're dissipating it. So you'd have to gain a lot of electric charge somehow, which I imagine you'd use light for that if you're in space, or really anywhere. You'd have to be able to gain electric potential energy in order to discharge that electric potential energy. And so you'd have to be doing kind of both of those things at the same time. You'd be gaining electric charge and then dissipating the electric charge so that you can go where you want to go. Also, if you're interested in these kinds of things, I swear there's a really cool video online that has been online for a good while, and it has to do with these, like the standing wave theory for sure. I think this guy kind of has shown the physical principles of both of those things, and the name of that video is the Hutchison Effect. So if you research that on YouTube, you will see a far more interesting video than this one, but it will show you all sorts of weird stuff about what this guy does with electricity, and basically it's crazy. Alright, everybody, so thank you for watching all my out there thoughts and theories. I hope you enjoyed, and I hope you check out the Hutchison Effect video. Leave a comment about whether or not you agree or disagree. I hope that you guys have your own opinions of this stuff and you don't just take my word for it. Anyway, shout out to my family. I love you guys. Everybody who watches and supports, you're the best. Know that next episode should be coming out around December. Hopefully it's going to be about mainly black holes and stars and things like that. It's going to be called Sources and Sinks. Should be entertaining. I hope that y'all have a great one.